It's now time to start our next talk. So welcome everyone to the talk titled Modern Advancement in NLP Fine-Tuning to be given by Armen Aghajanyan. A brief bio about Armen. Armen is a research scientist at Facebook AI Research focusing on advancing pre-trained representations for zero shot prompting and developing novel techniques and theories in the field of NLP fine tuning. So Ahmed is going to take up the stage for the next 30 minutes. But if you have any questions during the duration of the talk, kindly put it down in the chat. I'll relay it back to Amen, and he will answer that at the end of the talk. So Amen, you have our attention. Okay.
Thank you, Frank. Hey, folks. Thank you for joining. I'm Armen, so I'm a research scientist at Facebook AI Research, as Franklin mentioned. So the two main topics that I focus on in my research is how do we get better pre-trained representations, whether it just be for fine-tuning for Facebook's production purposes or zero shot, which is kind of what all the hype is right now with like GPT-3 and such. And then the secondary research that I use around fine-tuning. So I think for a lot of folks, fine-tuning is more important, especially in a production setting. So we're going to be talking about recent or modern advancements in fine-tuning. So we've seen this pattern a lot, right, with language models. That pre-training essentially focuses on scale, and we've kind of seen this exponential growth since Elmo came out in 2018, with everyone trying to get bigger and bigger models. And actually, this slide, which was adapted from Mile Out from Facebook Research, is actually outdated now. We're able to train past the trillion parameter models in certain cases. So what does this mean for NLP in general? Well, it turns out that there's a modern NLP recipe, right? Which is you pre-train the biggest model you can on as much plain text as you can. Or you just go to like Hugging Face, for example, and pick out a pre-trained model from there. And then if you have some data for production purposes, you fine-tune this data on a small amount of labeled supervised data. And you can pretty much repeat this for every task you see, and you get amazing performance every time. You really don't have to do anything clever, and you'll always be a couple points behind state of the art, which most of the time is not worth investing the disproportional effort in. But even though we have a very, very successful modern recipe, there are many open questions. One is, okay, we have these pre-trained representations that capture world knowledge. Well, how much of that world knowledge is actually maintained when you're fine-tuning on the end task? Is there a reason why we have to repeat for every new task? Is there some benefit to learning on a ton of supervised data all at once? And kind of the last question, which is personally my favorite, is why does this work at all? Shouldn't these giant models massively overfit? Pretty much any classical ML 101 class will talk about overfitting when you're over-parameterizing your models. But for some reason, this doesn't happen here. And a lot of people, pretty much everyone doesn't understand why this is happening. So I'll be talking about my paper, which was awarded Outstanding Paper this year at ACL, which kind of tries to answer this question. So before we get into it, I want to talk about what the agenda would be for today. It's quite dense. So we'll be focusing mostly on 5 things with a little discussion at the end. So we'll be talking about traditional fine-tuning and the intuitions that we have behind fine-tuning. We'll then talk about why the traditional approaches towards fine-tuning aren't necessarily correct, and why recently proposed adversarial approaches are probably better. We'll explore on the impact that fine-tuning actually has on the language model representations. And then we'll look at the topic that I think a lot of people are interested in, which is multitask learning. Why does it work? When does it work? And why doesn't it work in some cases? The 5th question will be, why does fine-tuning work at all? So this will be going through this paper at ACL that we presented. And kind of the last thing that we'll talk about, and it's a question that's been asked a lot, which is, with GPT-3, prompting is the thing. And I think there are a ton of successful startups that are using prompting style GPT-3. So the question is fine-tuning a thing of the past? I don't think there's a correct question here, but this will be more of a discussion a little bit. So what do we mean by fine-tuning here? So pretty much what this means is that we have some function, which is this pre-trained representation, that takes in a bunch of text, and then it outputs some vector or some time-dependent vector that represents this piece of text. And then what we do is we learn this classification head that pretty much does classification on top of these pre-trained representations. And this is pretty much the de facto way of training classification models on NLP right now. So in the case of generation, if you're generating, you can kind of assume that the classification head is just an identity, and then you're just fine-tuning the kind of the last layer if you want to learn how to do summarization, for example. So what intuition do we have when we talk about fine-tuning? Well, the main thing that pretty much everyone talks about is we want to stay close to the pre-trained representation or the generalizable solution. And this kind of makes sense, right? Why would you pre-train, waste so much compute if you're just going to move really, really far away from the original point? Might as well train from scratch. Yet, kind of funny enough, we know that gradient descent, stochastic gradient descent doesn't do this. Even for fine-tuning, it doesn't do this. So it turns out that the longer you fine-tune, the further you move away from the original point. So this intuition is kind of wrong, but we can reframe it to be right. So what does close mean? So traditionally, you look at the Euclidean difference. So this is pretty much just looking at the difference of parameters. And what's important here is that this doesn't actually capture the difference in function behavior. So let's look at this little animation to figure out exactly what I mean. So imagine you have your time step t that you're optimizing, and your theta t, which is your parameter, and then your f of theta t, which is your function, right? Now, what you can have is you can have a theta t that's pretty much the same for two different functions, yet the KL divergence is going to be infinity here. So let's look at the second function. So if we do the same thing for the second function, we have this delta of theta t being 15, but here the callback divergence, the difference between the functions, is actually quite small. Okay, so what does this mean? So essentially means that you can have a point that's the same space away, same distance away from a pre-trained representation, but yet the functional difference is very, very different, right? So what does this mean? The intuition here is that maybe we should be defining close, not necessarily in how far the parameters move away, but how the functions, a distance in the functions, a probabilistic difference, how different the two distributions are parameterized by theta t. So this seems like the correct approach. So we want to define close in this functional space. And kind of the very next intuitive thing to do is we want to bound every gradient descent step to just move a very, very small amount in this functional space. So what does this mean? We can pretty much guarantee that you're only changing the distribution of the pre-trained representations a little bit. Even though you might be changing the parameters a ton, the output distribution is about the same, or very, very small epsilon distance. So this is pretty much what this statement means here, which is you take a step, which is this delta theta that SGD provides you with the additional constraint that the distributional shift that happens is very small of the pre-trained representations. Well, this is actually really old. This dates back to the 90s with Amari and natural gradients. And Bengio and his team showed that this is equivalent to a very classical technique called natural gradient. And so what natural gradient tries to do is it tries to take steps in the probability space, but not necessarily in the parameter space. So this is really cool because we're pretty much taking a bunch of literature. Reinforcement learning has been using this for like 10 years now. They call it trust region. So now we kind of have this really cool method that we can apply to fine-tuning. And this is essentially what adversarial approaches are to fine-tuning. So I think the most popular paper right now that did this was the SMART paper that came out of Microsoft Research. And pretty much what they did is they found a really efficient way to calculating this natural gradient. And pretty much what you do is you sample a point during your fine-tuning. You sample a point close to your current parameter, and you try to see what the difference is, and you try to directly optimize this. But they have this additional step here that they do, which is they try to find an even better point that maximizes this distance. So they call this mirror descent in the paper, also a very classical technique. In our paper that we published in ICLR of last year, we showed that you can do something even simpler. You don't even need to do this supremum. You don't need to find the best point in order to calculate this maximum distance. It's good enough to sample randomly. But we found out that you need an additional constraint that's really, really important. And then, so we have a proof in the paper, but we want to change is what we want to bound is a change of representation in the pre-trained model, which is this f of x. Yet pretty much a lot of the adversarial approaches, they apply this on the classification head on top of the pre-trained representation. And it turns out that mathematically that's not correct. So in our paper, we proved that if you do want to do natural gradient or this adversarial fine-tuning on the classification head, you have to have this additional constraint, which is you want to make sure the classification head is smooth. In our case, you want it to be Lipschitz less than 1. Otherwise, you have no guarantees. So this was a small but very important detail that was missed on by a lot of previous adversarial papers. So a question that I think a lot of people had was, can we improve over glue? This is a standard classification. It's a benchmark pretty much consisting of 7 or 8 classification data sets. So it turns out that, yeah, unilaterally we improve over standard fine-tuning, which is what this standard is. These are our methods. We improve over smart pretty much half the time. And really the important thing for practitioners here is that our methods improve over the median runs. So a lot of times you don't have a lot of compute. You don't want to run best out of 10 seeds and then take the best model. So median runs are much better with our method, with this adversarial method. The other thing that we kind of showed is that we're a lot more resilient to changes in random seed, which again I mentioned is really, really important. Now, the second kind of thing that we tested on was cross-lingual, and this is actually really important because if you want to train only on English, but you want to apply it to like French and Spanish and German, for example, it's actually really important that you stay close to the pre-trained representations because otherwise you'll lose all cross-lingual capabilities, right? So what we showed here is that we can actually get, state-of-the-art cross-lingual numbers using XLMR, which is a very common cross-lingual model, without actually needing any novel pre-training method. So this was really cool. So we got state-of-the-art using XLMR large, and at the same time, InfoXLM came out of Microsoft that had the same numbers as we did, which was kind of cool. So it really shows the importance of fine-tuning correctly and not just doing standard fine-tuning. Otherwise, you can get into the mode of, we need better pre-trained representations, which sometimes is not the case. And let's see. Well, yeah, how good do we do for generation? So specifically, we looked at summarization, and then we kind of saw the same pattern. We take good old BART, and then if we apply adversarial methods on top of it, we get state-of-the-art in all of the tasks that we tried out. And we even beat out pre-trained methods that were specifically tailored for summarization, like Pegasus and Urgen. So quite impressive. I think the key takeaway here is that we need to be more careful about how we do fine-tuning. And it turns out that fine-tuning impacts the pre-trained representations a lot. So we get this phenomenon called representation collapse. So we actually degrade on the generalizable representations if we don't fine-tune carefully. So here, pretty much what we did is we froze pre-trained representations after we fine-tuned on the task, and we saw that if we just probe certain tasks, we actually get really, really bad results, which kind of shows that fine-tuning actually degrades representations. But if you use our methods or adversarial methods, it degrades less. But the numbers are still pretty bad, so there's still a little bit of work to do here. Okay, let's switch gears a little bit, and let's talk about multitask learning specifically. So when we talk about language modeling, we're very rarely actually sampling n tasks, which is why we need relatively large models for zero-shot prompting. And so the goal of pre-training is to learn representations whose distribution support, whose support of the distribution pretty much covers all NLP tasks. So we can actually visualize this. So let's say that we have this pre-trained representation, f of theta t, and we want to adapt it to either task 1 or task 2. So if we fine-tune on task 2, what's going to end up happening is that we shift the representations of f towards task 1. And actually, if we train in sequence, we'll shift over task 2. And so the variance of our pre-trained representation here actually reduces. And this is what we call representational collapse. So what can we do to do better? Well, we can do multitask learning. So we can move f data to the center of the tasks. And pretty much this would guarantee that we would have to move very little in order to fine tune. So this is what multitask learning kind of promises us. So what are the historical challenges to multitask learning? Well, it turns out that many papers have tried to incorporate multitask learning. So MTDNN from Microsoft tried it, T5 tried it. It showed that it degraded performance. Kushabi showed that if you do Q&A, if you do multitask learning in a very specific domain, and then you kind of massage the data to make it all look kind of the same, then you can get gains. But the thing that was interesting is no paper really looked at more than 10 tasks. So our group, we set out to do this largest multitask training setup ever. And so we call this multitask learning of this scale for the purpose of end-task fine-tuning, pre-fine-tuning. And this is a paper that we published in EMNLP of this year. I'll have links at the end of the talk. So pretty much what we did is we picked a set of 50 data sets across classification, summarization, MRC, which is just machine reading comprehension, and common sense, so common sense reasoning, so like NLI. And we had about a total of 5 million data points. So we ran into a couple of challenges. So the very first challenge is that there are different loss scales and the data set sizes are different, and that's historically made MTL training very unstable. So our solution to that is we scale the loss so that if a model predicts every class equally, that they will all have the equivalent values. So this is just equivalent to normalizing by the entropy of the distribution, which you can calculate very quickly. The other thing is that MTL tasks may have competing objectives. So you might imagine that if you do summarization, you might have gradients that point in the opposite way of like NLI or sentence prediction or sentiment analysis. So what we want to do is we want to fix this, and it turns out the solution is quite easy. If you have a ton of tasks, we just ensure that each batch of our model has multiple tasks. So we call this heterogeneous batching, and it turns out that this works really well. And we have statistics about this in later slides. And it turns out if you take Roberta, for example, and you do this type of pre-fine-tuning, this massive scale multitask learning, you actually improve on everything. We actually released these models, so they're available on Hugging Face if you want to go use the pre-fine-tuned versions of Roberta. So, for example, on Glue and on Squad, we improve on Bull Q, which is a sentence prediction task, a ton of common sense tasks. We improve over 3 summarization data sets almost unanimously. We kind of went crazy with all the benchmarking that we did. And even more results if you do structured prediction tasks, chunking, parsing, part of speech tagging, we improve over all that. And again, we improve over more summarization data sets, specifically ones that are not available in the pre-training data. So they're a little out of domain. And we improve over ANLI as well. So this is adversarial and NLI task that historically has been very tough. So we show small but relatively significant improvements there. So unanimously, we show that if you're using pre-trained representation, using ones that were pre-fine-tuned will probably give you a little more boost, pretty much for free. They're the same model, right? So you just change model paths and you get gains, which is pretty much the most perfect thing in a production setting. And the other kind of thing that we showed is that the scale is actually really, really important here. So if you look at this, the x-axis is pretty much what percentage of the data we use. The y-axis is how many tasks we do multitask learning with. And if you look here, if you go up to 16 tasks for multitask learning, you're actually going to degrade performance. And this is pretty much consistent with what like T5 showed, right? But it turns out that if you go up towards 35, 40 tasks, you improve. So it turns out that there's this critical point, and the people that have had challenges with multitask learning have been working in this critical point. But the moment you break out of it, multitask learning kind of becomes really, really easy. So unsurprisingly, the key here is scale. But yeah. The other thing I wanted to talk about is how important it is to mix batches. Doing tasks in sequence isn't super great. So you actually want to mix all your batches together. So this is kind of what we showed here. So training, the blue bar is training data sets in sequence. The orange one is every batch contains a single task, and green is ours, which is every batch contains dozens of tasks. So this is kind of the other secret to getting multitask learning to work. And I think, again, we improve unanimously across all different styles of batching. Yeah, and now let's talk about, we're going to switch gears a little bit and then move to, why does fine-tuning work at all? So we saw that if you do adversarial training or fine-tuning on top of pre-trained representations, it improves. If you do multitask learning, it improves. But all these improvements are rather minor, right? They're in a couple of points. We're not talking about tens of points. The majority of gain actually comes from these pre-trained representations. So the big question that I think a lot of people have is, how are we able to fine-tune these billion parameter models on 1,000 data points, or sometimes even on a couple of hundred data points, without overfitting at all? So this is actually a really, really hard question to answer. And so the surrogate question that we wanted to answer was, how many parameters do we really need in order to fine-tune and still be able to generalize? So the distinction here is you can still have, a billion parameter model, but it might turn out that you only need to fine-tune like, 100 parameters. And then it kind of makes sense, right? If you only need to fine-tune 100 parameters out of this billion parameter model on 100 data points, it kind of makes sense why we're able to generalize so well. So before we jump into what this paper analyzed, I want to talk about intrinsic dimensionality. So we actually didn't discover this concept. This is quite an old concept. It was applied to machine learning in 2017 or 2018 by Lee and Al in their paper, Measuring the Intrinsic Dimension of Objective Functions. Yeah, let's talk about this. Let's go through the background here. So the kind of toy example that we use here is that, you might be optimizing in this three-dimensional space, right? But if you're doing SGD, it might be that, you're taking a straight line from, your starting point to your final point. So what does this mean? Well, it means that we're actually just optimizing in this two-dimensional space. So we need to figure out a way to formalize this. And pretty much what we do here is we can reparameterize the full space by pretty much fixing the original parameters and then projecting from a very low dimensional space, which we call little d, to big D. And this projection is a fixed linear projection. And we'll talk about exactly what this projection is in a little bit. So by doing this, you're effectively optimizing on this two-dimensional plane, but you're actually projecting it onto this 3 dimensions. Okay, so what's the analogous terms here to fine-tuning? So data big T is pretty much the reparameterization of all the weights that we have for fine-tuning. Data D0 is the original fixed pre-trained weights. So for example, you could be using BERT, Roberta, BART weights. Data D is the one parameter that we're actually optimizing. So we call this the learnable intrinsic vector, and it has a small dimension of D. And D is very, very small. It can be in the hundreds. And P here is a fixed random projection that projects from small d to big D. So what is this projection going to look like? So kind of the trivial thing to do is, we can project it just using a dense matrix. So this is pretty much just a linear projection, like a linear layer. This is actually quite problematic. So using dense matrices actually does not scale at all. So doing this type of intrinsic optimization with small d being 1,000 for Roberta, this would require 1.5 terabytes of memory. And that would be just to store the random projection. To compute it would be much more. So we need an alternative here. So what's the alternative approach? Well, one thing you could do is you can use very sparse matrices. This actually works. It solves some problems, but sparse matrices are a huge pain to work with. They come with their own host of stability issues. So we needed an alternative here. So the alternative was to use something called this fast food transform. So we don't have to dig super deep into this, but it's still a linear transform. And we pretty much just use properties of Hadamard matrices to speed up computation. So the space complexity is, O of big D, so we have to store an extra copy of the model. Not too problematic because, optimizers like Atom, they store like 4 copies of your model. And the time complexity isn't bad. It's also pretty much linear in big D, given that small d is very small, so taking the log of it is going to be tiny. And the fast food transform is actually quite fast. So this helps a little bit. The other thing I want to talk about is we actually changed the parameterization a little bit. So in this classic intrinsic reparameterization, you actually don't care about layers. You don't care about depth at all. And this is quite problematic for pre-training because, there have been a ton of papers that have looked at pre-training and saw that, fine-tuning later layers is more important than earlier layers. So we wanted to encode this in depth of prior. So the way we do it is we actually we trade off some parameters from this intrinsic vector just to be able to scale the impact of certain layers. And we call this structure-aware intrinsic dimension. So pretty much for every ith layer, we introduce a learnable lambda I that does scaling. So this is kind of the background that we have. The key takeaway here is that we have a way to optimize in a lower dimensional space. That's kind of the main thing to take away. And we use intrinsic dimension to do so. So what are our contributions to this paper, in this paper? So there are a couple. So the first thing is that common data sets can be learned with a few hundred parameters. So this was a very, very surprising result. And it pretty much showed that pre-trained representations are doing something very, very non-trivial. And SGD and fine-tuning is also doing something non-trivial. We actually don't understand how it works at all. So yeah, the second point is that pre-training actually implicitly reduces the intrinsic dimension of downstream tasks. So here the intrinsic dimension is the amount of parameters that you need to optimize a certain task. And it turns out, paradoxically, that larger models have a smaller intrinsic dimension. So the more parameters that you have, the less parameters you actually need to fine-tune in order to get better results. And this makes sense all of a sudden as to why bigger and bigger language models perform better. Models with a lower intrinsic dimensionality perform better. They generalize better, both empirically and theoretically. So we'll talk about all this. Okay, so what we do here is we pretty much optimize from, I think, 100 parameters to 10,000 parameters in this very low dimensional space for two data sets, MRPC, which is, it's a paraphrase detection data set, and QQP, which is question similarity data set. So it turns out that, you can reach up to 90% of the full parameter solution. We call this the D90 solution, just by optimizing in 200 parameters. So this is quite insane. So this is pretty much saying that paraphrase detection can be solved using 200 neurons. I mean, it's not even enough to represent the embedding, but it is within the framework of Roberta. And we kind of see the same thing for QQP, where we only need 800 parameters to fine-tune QQP up to 90% of the full parameter solution. So this was a very, very surprising result that we have. And so the follow-up question that we asked was, okay, well, what does pre-training do to the intrinsic dimension of tasks? And so we look at, we pretty much took 17 checkpoints from Roberta, and we computed this D90 for 6 different tasks. And the cool thing that we see is that the intrinsic dimensionality pretty much monotonically decreases, implying that somehow the pre-training implicitly reduces the intrinsic dimension. But the thing is that it never actually sees these tasks in the wild, or sees them in very, very tail cases. So the fact that it's able to minimize something that it doesn't actually see is very, very interesting. And so the question we went from here is, okay, well, Roberta was fixed, right? In terms of parameter count. How does parameter count impact this intrinsic dimension? So unfortunately, we couldn't do the right thing of keeping, architecture and objective consistent, and then pre-training various sized models. It's just computationally way too expensive. And even at Facebook, we don't have that much compute to do like 50 large pre-training runs. So we pretty much went to the Hugging Face repo when we took all the popular pre-trained models, and then we plotted their intrinsic dimension. And we see this very strong inverted linear correlation, which is that the more parameters you have, again, paradoxically, you need a smaller intrinsic dimension. And the really kind of other cool thing that we see here is that within a certain band of parameters, the method of pre-training matters, but nothing actually trumps just having more parameters. So it might be that, we don't even need clever objectives, like mass language modeling scaled up is probably will have very good scaling laws, right? And that doing research, while only looking at a number of parameters may be worthwhile, but doesn't scale out super well. So this was quite interesting and kind of has an impact on our research directions as well. And the other thing we did is we took the absolute evaluation accuracy of checkpoints with different intrinsic dimensions on n tasks. And unsurprisingly, models that tended to have a lower intrinsic dimension performed better. And the other thing we looked at is the generalization gap. So pretty much what this is we take the best evaluation accuracy and then we compare it with the respective training accuracy and we subtract the two, take the absolute value. And so pretty much this gives us an indication of how well are we actually generalizing with respect to our trained set. And so the really kind of cool thing that we see again is that models that tend to have a lower intrinsic dimensionality end up generalizing better. So what we really wanted to do is we wanted to come up with at least some mathematical formulation as to why this works. So we call this our intrinsic dimension-based generalization bound. So pretty much what we do is we notice that this intrinsic reparameterization is deterministic in theta d. So you can actually kind of think of this as doing some sort of compression of a large model. And so if you do this, you get some really, really cool results. So if you treat theta 0d as fixed and the transformation as the fixed linear projection as a fixed string, we actually use a random seed to generate this. So it's actually one number. And then you can apply Sanjeev Arora's compression-based bounds, and we get this really, really cool result, which is that we get a result that says that we generalize pretty much as good as the square root of the intrinsic dimension divided by the amount of samples that you have. So if you have a very large intrinsic dimension, like a randomly initialized network, then you need a ton of data. If you have a very good pre-trained model where the intrinsic dimension is very low, you actually need small amount of data. And so these generalization bounds are actually fully independent of the parameter count of the full model. So this is really cool. This is the first time I think that we actually have some intuition about why, or some theoretical intuition about why these very large pre-trained models are able to generalize so well on such a small amount of data. So this is kind of the first result that I've seen that does this here. And kind of the big question that a ton of people have been asking, which is fine-tuning a thing of the past? This is an active research question. So far, no prompting approach has been able to reach the performance of full fine-tuning, even using relatively small pre-trained models. And realistically, one thing that we've seen here at Facebook is that natural language prompts, they seem to be out of domain for most language modeling tasks. And because they're out of domain, it's really, really hard to get good performance just by doing language modeling. We've tried a ton of stuff, so my main focus is on prompting. So in this recent paper that we published, which is called HTLM, we showed that if you do prompting in HTLM instead of natural languages, you can actually get really, really good performance. So this is state of the art right now, and here we achieve the same performance as fine-tuning like BART on 1K samples, But the moment you use 2K samples, our method's blown out of the water, right? So what I tell people now is for all production purposes, I think fine-tuning is here to stay, at least 2 or 3 more years, I think. We've had a really tough time scaling up prompting to be even competitive with Roberta. So yeah, fine-tuning is probably here to stay, in my opinion. So this is kind of the end of the talk. So we actually went through a ton of papers. So we went through 4 of the papers that I published in the last year. If you guys are interested, I'll leave the slide up while we take questions. You can go read these papers. Also, feel free to email me or message me on Twitter. I'm usually pretty responsive. Cool. I think there are some questions. So yeah, let's go through some of these questions.
Okay. Thank you so much, Armen, for the talk. Really appreciate it. That was an excellent talk and very informative too. Yeah, I think we'll go back to the questions. Quite a few of them here. From Simon Hughes, his first question. For a domain-specific task with a large enough corpus, do you see there being an advantage to training a deep LM from scratch on that data, using mask LM for EX, and then fine-tuning on some downstream tasks Or do you think in most cases there is still a benefit from using a pre-trained model?
That's a very good question. There is still some benefit to using a pre-trained model. In generally, we see that if you train an LM from scratch, um, even on, if you have like, even if you have like a half a terabyte of data, um, it's usually much better to train on a larger data set. So, for example, in our HTML paper, we train on 20 terabytes. But in general, what we're seeing this kind of pipeline that's happening if you have a domain-specific task, which is you take a pre-trained model, right, that's been trained on terabytes of data, huge, right? And then you do further pre-training. So there was a paper recently called "Don't Stop Pre-Training" that looked at exactly this. So you do further pre-training on domain-specific data, and then you can do what we did, which is pre-fine-tuning, and then you can do fine-tuning. So this kind of 3 or 4-step approach, which is you pretty much slowly increase the amount of information that's domain-specific in your data, seems to be the best way to do it. I've yet to see a deep language model trained from scratch on some domain-specific data. Usually, if you have domain-specific, it means it's usually pretty small but informative. So yeah, I think pre-training is probably here to stay. But I think these steps that I mentioned, which is you don't stop pre-training, you continue pre-training on a domain-specific subset, you do pre-fine-tuning, you do massive multitask learning on your data and other people's data, and then you do fine-tuning on your data. I think that's the pipeline that's going to stay for production. Let's go to the next question.
To the next question, Jerome Massot. That's a question. Like, why do people continue to criticize overfitting during fine-tuning, whereas overfitting is very often needed to move from passable performances to a minimum business metric needed for industrial usage?
Yeah, so one way I think to look at it is, I mean, in a production case, right? Like even when I work on production teams, at the end, all you care about is your test set performance. There are a couple of reasons. One thing, in generally, if you're overfitting, usually you have smaller end evaluation accuracies. That's kind of the first thing. The second step is we see with overfitting, it becomes highly problematic. There are like ethical concerns with highly overfitting. Most of the time, you're going to be able to regurgitate some data, or it becomes hyper specific to the data that you trained on. So it might turn out that you deploy this model, and it works for like 2 weeks, but then there's a small domain shift, and all of a sudden your data set will break, or your model will break. It's very brittle. So there's a ton of issues with overfitting and robustness. I think the two are very tightly coupled, and I think there have been some recent papers that have been looking into this. But again, at the end, you always want to pick what the best evaluation accuracy you have is, assuming that you have the proper data splits and such. But I think overfitting is still kind of important for the reasons that I mentioned. Let's see. I think, Franklin, you're cutting out. But yeah, so for the third question, is there a relationship between your findings on intrinsic dimension and very few tunable parameters to the mammal paper on functional learning? Yeah, so mammal kind of does meta learning, right? So actually, pre-training and meta learning are quite similar. I mean, the whole goal of meta learning is you want to pretty much come up with an objective that gives you a good enough initial point that you're close enough to moving to any of your tasks. And this is actually the exact goal of pre-training. We're just taking different routes to do it. And I think it is kind of aligned. Mammal puts you in a good enough place that you can do very, very few shot learning. I think moving to the center of all of your tasks is also kind of the promise.
The next question by Simon is there a relationship between your findings on intrinsic dimension?
Sorry, I think Franklin couldn't. Yeah, Franklin, sorry, I'm taking this question right now. Sorry, where was I? Yeah, so multitask learning, in order to bring it to the center of the distribution, kind of does the same thing that mammal does. So I definitely think there's connections between meta learning and pre-training. I haven't seen any paper that does it yet. So for any PhD students you're thinking about a follow-up paper, I think that's a really interesting task to take on. Okay, I think we have another question from Wafa. Let's see. With more research on prompt engineering,
Okay, no problem.
can it dominate over fine-tuning? Yeah, I don't know, maybe. I've played around with prompting a lot. I've been working on this for like 8 months now. I think figuring out the pre-trained representation that's in domain for prompts is the big question, which is we thought that HTML, because you can represent tasks also in HTML, would be more in domain, and we had kind of some success there. Um, but the question is maybe. I mean, the kind of NLP North Star, right, is you want to be able to write a task description, even a complicated one, right? Um, Imagine like you're doing integrity at Facebook, right? So you have these very huge description for what constitutes an integrity violation, and so we have to send those out to crowd workers, and they come back and they give us this data, and we train our models. The the North Star for us is can we replace that whole process, right? Like, can we give a model a prompt that's pretty much what we could give to like a mechanical turker, uh, and we would be able to, with zero shot performance, get something similar to fine tuning. That's the dream. I hope that we can get there. I mean, inevitably, I think we have to get there. That's the direction where everything is going. But I think it's going to take some very clever breakthroughs. And I'm not sure if just scaling up our models on more and more data is the answer. At least from what I've seen internally, it is not the answer. Okay, I think there's a follow-up question from Wafa, which is, are large language models doing understanding or pattern matching? Yeah, that's a fantastic question. What I've seen is pattern matching. I don't think they actually understand language. And there's a higher philosophical question is like, can you understand language without actually grounding in reality? So our language models don't actually ground in like videos or images. Um, so that's actually a project that I'm working on now, but I don't think they're doing language understanding of any sort. There's been a couple of papers that showed that models like BERT do very deep co-word factorization. So you can think of them as just an extension of like word2vec, where word2vec takes just co-occurrences of two words and then does matrix factorization. BERT does this with like n-grams or paraphrases. I think there was a paper that looked at this that actually showed that positional information is not even too important. So I definitely don't think they're pattern. I don't think they're understanding at all. I think it's completely pattern matching. Does this affect reliability in sensitive production cases like law or health? Yeah, I think you should be very careful if you're deploying these models in law or health. First thing is, having just one evaluation set is not correct. You need view sets of your test data sets. Again, for like checking bias, all of these models have bias. So yes, you shouldn't assume that they understand everything. You should, the default mode if you're working in a sensitive production case is to assume that in some sense these models are adversarial, and you need to do a lot to filter them to work fairly. Can we, I think Simon mentioned, can we use knowledge graphs to tune or enhance language models in some way? Obviously, the inverse is being researched. Yeah, actually, I think there was a recent paper, and to be fair, just I haven't actually read this paper in detail, but I think the Ernie Gen 3 paper looked at how they can use knowledge graphs to enhance language models. I definitely think we can. I think at the end, it's all about data curation, right? Like if you just train everything on Common Crawl, um, you're gonna, you're gonna get data that's wrong, right? Stuff like genocide denial is rampant, right, in Common Crawl, and it's hard to curate this data well. And there have been efforts, right? Like Luther AI has released this pile data set, which is this very carefully curated data set. But still, I don't think that's enough. And knowledge graphs are the peak of curation, right? It takes a lot of time. I've actually worked on knowledge graphs before. It's a huge human effort to get correct knowledge graphs. So this is a very interesting direction, and I think folks are already looking at this as well.
That's great, Armen. I'm just going to jump in for Flanken. So thank you so much for answering all the questions and also for the great talk as well too. And thanks everyone for attending this talk. And if you have any follow-up questions, please feel free to reach out to Armen on LinkedIn. Once again, all of the sessions are recorded. And thanks everyone. Thanks, Armen.